Next on the agenda is a technical talk by Dr. Venkateswara Pai. Dr. Venkateswara Pai is a distinguished physicist. He possesses a profound command of technical Sanskrit and Malayalam. He earned his PhD in the history of astronomy from IIT Bombay, with expertise spanning Sanskrit, mathematics, and astronomy. Dr. Pai conducts multidisciplinary research focusing on unraveling the contributions of the Kerala School of Astronomy and Mathematics. His investigations involve the meticulous study of source materials found in palm leaf and paper manuscripts documented in Sanskrit and Malayalam. Currently serving as a professor at IISER in Pune, Dr. Pai is also a respected member of various national level committees dedicated to Indian knowledge systems. Dr. Pai, we look forward to your technical talk. Jai Bhagwan Yogi Ramsuratkumar.
Namaste. First of all, I thank the organizers for giving me an opportunity to talk. The title of the talk is The Vakya System of Astronomy. Professor M.D. Srinivas has given a wonderful overview of Indian mathematics and astronomy. So I would be talking about a specific school called the Vakya School, which is originated in Kerala and developed and mostly popular in Tamil Nadu region. So Professor M.D. Srinivas talked about the texts such as Aryabhatiya, Siddhanta Shiromani, and so on. So they come under the category of literature known as Siddhantas. So the the huge corpus of Indian astronomical literature, what do I mean by the comprehensive astronomical literature, has been found from 5th century, and the earliest text that we can trace back is Aryabhatiya. And the Aryabhatiya, Siddhanta Shiromani, etc. fall under the category of Siddhantas. So there are two different classes of literature that we can find in Indian astronomical literature, that is Siddhantas and Karanas. Siddhantas are more comprehensive, more mathematically complex, and the Karanas are practical manuals. Similarly, we have two more categories which are mentioned in a text called Vakya Karana, which talks about the Vakya school. That is called Tantra and Mahatantra. So the Vakya system is a separate system which makes use of Vakyas or sentences to obtain different astronomical parameters. So now what is Vakya? So Vakya literally means a sentence consisting of one or more words. In the context of astronomy, it refers to a phrase or a string of letters in which numerical values associated with various astronomical parameters are encoded. So the Vakyas are composed using Katapayadi system of numeration. Professor Srinivas already talked about Katapayadi system. In brief, I will be talking the system in little bit more detail. So there are three systems of numeration that Professor had talked about, that is Bhuta Sankhya system, Katapayadi system, and Aryabhatan system. So one of the system is Katapayadi system of numeration. The Vakyas are composed using Katapayadi system of numeration. So the strings used in composing Vakyas are chosen so that they not only represent numerical values, but are also in the form of beautiful, meaningful phrases and sentences that convey worldly wisdom and moral values. For example, these are the earliest set of Vakyas that we can trace back. These are known as Girna Shreyadi Vakyas. So the Vakyas look like this. The professor also talked three of the Vakyas. Girna Shreyaha, Dhenava Shrihi, Rudrastu Namyaha. So we have 248 such Vakyas. Rama Giyate, Atyaharastu, Kavehe Shakyam, Bhavet Sukham. So these are known as Vararuchi Vakyas because it's composed by Vararuchi. And we can trace back this to 5th to 6th century AD or CE, Common Era. So now this is also known as Girna Shreyadi Vakyas, means this starts with the Vakya Girna Shreyaha. And obviously the Girna Shreyaha has a meaning, Dhenava Shrihi has a meaning, and these are all meaningful phrases. However, in the context of astronomy, these represent some numbers. For example, the Girna Shreyaha is 001203, which means 0 Rashis, 12 degrees and 3 minutes. Dhenava Shrihi is 024 9, that is 0 Rashis, 24 degrees and 9 minutes. And up to Bhavetsukam, we have 0, 27 and 44, that is 0 Rashis. Here 0 is because of, if we split this into 4 syllables, we have these 4 numbers 1, 2, 0 and 0, 3. And there is the absence of 2 more syllables that represents number 0. Whereas if you look at the third Vakya, Rudrastu Namyaha, there we have 5 syllables which represents 0, 1, 0, 6 and 22, which is nothing but the 1 Rashis, 0, 6 degrees and 22 minutes. These Vakyas, what are these Vakyas? These are 248 number. These are known as Chandra Vakyas, Vararuchi Chandra Vakyas or Girna Shreyadi Chandra Vakyas. So these give the mean the true longitude of the moon from first day to the 248th day. So when we memorize all these Vakyas, as said by again Professor M.D. Srinivas already talked about this, we can suppose if I want to say find the longitude of the moon on 124th day, you can just memorize and reproduce Ramagiyate, and if you know the Katapayade system, we can decode the number from Ramagiyate, and that number would be 0, 6, 13 and 52, which is nothing but 6 Rashis. The moon's true longitude is 6 Rashis, 13 degrees and 52 minutes. When I say 6 Rashi is the zodiac. When we divide ecliptic into 12 parts, one part is known as zodiac or the Rashi, and that is equal to 30 degrees, and 1 degree is equal to 60 minutes. The minutes, these are arc minutes. Okay. So now, in order to understand the numbers encoded in these Vakyas, we need to know the Katapayadi system. As Professor has pointed out, so Katapayadi is nothing but Katapaya Adi. Adi means etc. So Katapaya represents 4 consonants in Sanskrit alphabet. Katapaya, which means Kadi, Tadi, Padi and Yadi. When I say Kadi, it's Ka, etc. We have to count number 1 from Ka, and Ka becomes 2, Ga, Gha, Nga, Cha, Cha, Ja, Ja, Nya, goes up to 1, 2, 3, 4, 5, 6, up to 0. Then again, Ta, Ta, Da, Da, Na, Ta, Ta, Da, Da, Na, 1 to 0. Then Pa, Pa, Ba, Ba, Ma, 1 to 5, Ya, Ra, La, Va, Sha, Sha, Sa, Ha, 1, 2, 3, 4, up to 8. So here only consonants have numerical significance. In the case of Tamil system, Professor talked about it, the number corresponds to the vowels, but here it is only consonants have numerical significance, no vowels have numerical significance. However, the standalone vowels represent number 0. So let's see an example. Let's take a string or phrase called Chennai. So what one has to do is we have to split this into 2 subunits. So we have Che and Nai. Now the number associated with Cha is 6, whether it's Che or Chi or Chu or Cha, it is only 6. And number associated with Na is 0. Again, here there are 2 Nas, because this is called conjoined consonant. There are 2 Nas. Only we have to consider only 1 Na, which is more proximate to the vowel. So the Na which is proximate to the vowel has to be considered here. So Na is 0. Now when we reverse the order, we have number 06, that is associated with the string Chennai as per Katapayadi system. So now let's take another phrase, IIT. So again split this into syllables. I means it's a vowel, that's 0. I again is 0. So Ta is 1. When we reverse the order, we have 100. The number associated with IIT is 100. So this is how the Katapayadi system works. So when we apply this system here, so here we have Girna Shreyaha. Ga represents 3. Na represents Gir Naha. Na is the consonant approximate to the vowel, so it's 0. Then Shra, that is Ra, is 2, and Ya is 1. When we reverse the order, we have 12 and 03. So 12 degrees, 03 minutes. And these represent true longitude. When I say true longitude, it is nothing but the true position of the moon from a fixed point. And the fixed point here is nothing but the beginning of the Mesha Rashi or the beginning of the Ashwini Nakshatra. Okay. So now, So in Siddhantic, so in order to appreciate the Vakya system and the algorithm for finding the, we'll be concentrating on finding the moon's longitude for an arbitrary date using Vakya system. So in order to appreciate Vakya system, we should know a little bit about how Siddhantic procedure works. In Siddhantic procedure or algorithm, first step is to find the Ahargana. Ahargana means, Gana means group, Ahar means, Ahaha means day, here day means civil day. Civil day is nothing but time period corresponds to 2 consecutive sunrises. So when I say Ahargana, Annam Ganaha, that is group of civil days. So group of civil days from an epoch, and epoch is usually chosen as the beginning of Kali, which is 3102 BC, February 18, in Siddhantic texts. So the Ahargana is the number of days between this epoch, that is the beginning of the Kali, till the desired date. When I say desired date, what do I mean by that? Desired day means when suppose I want to find the longitude of the moon for today's date, today is the desired day. So the Ahargana is the number of civil days elapsed till today from the beginning of Kali. And that has to be multiplied by the number of revolutions made by the planet. Suppose if you want to find the longitude of the moon, we have to multiply the number of revolutions made by the moon in a Mahayuga, which is given in the text, and it has to be divided by the number of civil days in a Mahayuga. So which will essentially give the rate of motion per year, and that per day, that has to be multiplied by Ahargana would give the mean longitude of the moon. Once we get mean longitude, we have to apply a samskara called Manda Samskara, which is nothing but the eccentricity correction, which takes care of the eccentricity of the elliptical orbits. Because the Indian assume that the planets are moving in a circular orbit, and the procedures are based on assuming the circular orbits of the planets. Then we have to apply the eccentricity correction, that is known as Manda Samskara, to obtain true longitude of the planet, that is theta, in terms of theta 0, that is the mean longitude of the planet, minus delta theta, that is the correction term. And this sin delta theta is r0 by r. This is again the parameters which are given in the text, which is known as the epicycle ratio of the epicycle radius to the different circle. So now here the theta 0 is the again mean longitude of the planet, and theta u is the mean longitude of its apogee. So when I say apogee, it means suppose here let's take the case of moon. So here is Earth. Moon is revolving around the Earth in a circular orbit. So when it reaches at this point, that is, this is given as moon's direction of moon's apogee, it will have the least motion. So the mean longitude of the moon as well, the longitude of the moon as well as its apogee is same in this case. So the eccentricity correction is actually a function of the difference of mean longitudes of the moon and its apogee, that is known as Manda Kendra, or longitude of anomaly. So now in Vakya system, so the basic text of Vakya system is known as Vakyakarana, which is of 12th century. The author of the text is not known. They first give a parameter known as Khanda. Khanda literally means a part. So the Vakyakarana, the text Vakyakarana gives this as a phrase, Vede Dhat Jnana Tushtaha. So again, as per Katapayadi, this amounts to 1600984. Khanda is again a part of, Khanda means part of Ahargana. So it actually the contemporary Ahargana where the moon is in conjunction with its apogee. Obviously, moon is in conjunction. Moon will be in conjunction with its apogee in every 27 days. However, the Khanda is chosen in such a way that the time of or the instant of conjunction is more close to the instant of sunrise. So now the text also gives what is known as dhruvas. Dhruva literally means stationary, and in this context, dhruva is a constant value. It's nothing but the constant value for the true longitude. So there are 4 such dhruvas are given. So the Senanarinathanam, Nityadeva Sukhadinam, which amounts to 7 rashis, 2 degrees 0 minutes and 7 seconds, that is nothing but in degrees 212.00194, and so on. So these are nothing but the dhruva or the true longitude at the khanda. That is, this 160094 is the 160098 day from the beginning of Kali. So the moon's longitude on this day is 212.00194. And this dhruva 297 is 297.80272 corresponds to the longitude or the bhukti, which is known as corresponds to 12,372 days. Suppose the moon starts its motion at 0 longitude. After 12,372 days, it will have moon will have the longitude of true longitude of 297.80278. After 3031 days, it will have 337.51694. So now, what are these values correspond to? These are known as anomalistic, the days for anomalistic cycles. So we will talk about this later. If you look at this table, you can see that so these large numbers, this corresponds to the number of anomalistic revolutions which made by the moon in these many number of days. Which means, suppose moon starts its motion from its apogee exactly at the time of sunrise, then it will take these many number of revolutions to come back to its apogee which also happens at the time of exactly at the time of true sunrise. So for that, the moon will take these many number of days. Okay. Now, so these smaller values are nothing but these successive approximations of these two values. So they are also nothing but in 9 days, in 248 days, moon completes 9 anomalistic revolutions. But they may not come back to the same, come back to the apogee exactly at the sunrise, which means there will be a time difference between the instant of sunrise and instant of conjunction of the moon and its apogee. Okay, so that's the significance of these numbers. So now, the algorithm for the computation of moon's longitude. Suppose we need to find the moon's longitude or the true longitude of the moon for an ahargana A, then what we need to do is first we need to find something known as khanda shesha. The term khanda is already defined. We will be again briefly defining that. The khanda is a part of ahargana, and as per Vakyakarana, that 16,00984 is the khanda, which means moon and its apogee, the conjunction of moon and its apogee happens close to the sunrise on that day. So the ahargana is the number of days elapsed from the beginning of Kali till today's date. We have to subtract khanda from this ahargana, that is known as khanda shesha. So now khanda shesha is nothing but a minus a prime, that has to be divided by 12,372. Then we'll have quotient Q1, we have to store this value, and we have remainder R1 by 12,372. So remainder is R1 here, Q1 is the quotient that is obtained, and this R1 has to be divided by, R1 is obviously lesser than 12,372, so this has to be divided by the next anomalistic days in next anomalistic revolutions, cycles of anomalistic revolutions. So R1 by 3031, that is Q2 plus R2 by 3031, and R2 is the remainder obtained here. So now R2, here again R2 will be less than 3031 and will be obviously greater than 248. So R2 by 248 we have to do, then we have Q3 plus R3 by 248. And here the R3 is lesser than 248, it can go up from 0 to 248, it can take from values from 0 to 248. So here we have to apply this Vakya, this Chandra Vakya. Okay. So now, so we have got these values Q1, Q2, Q3, etc. These are the quotients. These have to be multiplied by these corresponding dhruvas. Dhruvas are nothing but D1, that we have seen that the moon's longitude corresponds to 12,372 days. That has to be multiplied by the Q1, and it has to be added, and D2 multiplied by Q2 and D3 multiplied by Q2, and we have to add all these results. And this is DI, that has to be added to the D0, which is nothing but this is called as Khandantya Dhruva, which is the Dhruva or the true longitude, which is tabulated by the author. Of course, we could obtain that mathematically, but tabulated by the author, that is D0 at the Khanda. Okay. Now VR3 is the Vakya corresponds to R3, number R3, which is nothing but the remainder obtained at the last stage. Now let's, so these are the Girna Shreyadi Vakyas. Now let's take an example. Vishana will illustrate the procedure. The Vichu's Kalya Hargana A 1851 974. This corresponds to Nija Ashada Krishna Navami Shaka 1891. That is August 6, 1969 CE. So here A is, that is Ahargana is 1851 974. A dash is 1600 The Khanda Shesha is 250 990. Now first we need to find first quotient by dividing the Khanda Shesha by 12372. We get 20 as the quotient, and the remainder here is 3550. That has to be divided by 3031, and the quotient 2 we get as 1, and this has to be divided by 30, and the R2 here is 519. 519 has to be divided by 248, and the Q3 is 2. 519 by 248 is again the R3 for this is 23. So here we have to apply the Vakya 23, and here Q1 is 20, Q2 is 1, Q3 is 2. So D0, we already know the value of D0. D1 multiplied by Q1 plus D2, we get, if we compute this, we get 81.00448 degrees. This has to be added to the number or the longitude corresponds to 23rd Vakya, which is nothing but Goraso Nanusyat, which corresponds to 10 Rashi 7 degrees 23 minutes, which is 307.38333 degrees. When we add this value to 81 degrees, we get the true longitude of the moon at the time of Ahargana, I mean on the day of Ahargana. Okay. So now the, so here, so we can see that all these computations have been done by considering that moon coincides with its apogee at the time of sunrise, but it's actually not happening. So there will be after 12,372, it's approximately, of course, on 12 after each 12,372 days, definitely moon will coincide with its apogee, but not at the time of sunrise. So there will be the finite difference, time difference between the instant of sunrise and the instant of conjunction of moon and its apogee. So there will be an error which will be accumulated because of this time difference, and also we have chosen Khanda by assuming that at the time of Khanda, moon coincides with its apogee exactly at the time of true sunrise, but again it's not actually will not happen. So there will be a finite difference between the instant of sunrise and the instant of conjunction. So all these errors will added up. So the text Karana Paddhati, so this is the Khanda. How much time do I have? 5 more minutes? Okay. The text Karana Paddhati gives 2 separate samskaras or the correction terms to address this issue. So they are known as Yogodayantara Samskara and Dhruva Samskara. So the text Vakyakarana does not talk about these samskaras. They just give the algorithm, also not the rationale behind this algorithm. The text Karana Paddhati of Pudumana Somayaji, it's a Kerala astronomical text composed during 1532 CE, gives all such algorithms rationale, all rationale behind such algorithms. So one such rationale is to find something known as Valyupasamhara, which is known as Valyupasamhara, which to obtain the successive approximation. I'm this is how the Valyupasamhara works. So since we don't have time, I'm just skipping this. And it also gives the rationale to obtain the Khanda for a contemporary date. And as I mentioned, there are 2 samskaras which is talked in the Karana Paddhati. There is Yogodayantara Samskara and Dhruva Samskara, the samskara which is applied to the Dhruva. There is another text called Vakyakarana of Parameshwara, which is different from old Vakyakarana. So Parameshwara is again Kerala astronomer of around 14th century, 1350 to 1435, during that period, that is early 14th century astronomer. So he has composed another text called with the same name, that is known as Vakyakarana, which is just 60. It contains 60 verses, and he just gives algorithms for just finding the longitude of the moon as well as the sun. In that context, he elaborates a discussion on Dhruva Samskara, where he gives the algorithm for finding the Dhruva Samskara, which is to be applied at the end of the once we obtain the value of true longitude of the moon using the Vakyakarana method. Vakyakarana here is old Vakyakarana method. So this is how this Dhruva Samskara, which is given by Parameshwara in his Vakyakarana, Aniya Tungamadhyendu Vakyarambha Dinodaye Tayorantaramaniya Tenendor Madhyamam Gatim Chandrocha Bhuktirahitam Vibhajet Labdhamatratu Dhruva Samskara Samjnaha Syat Harakaha Swarna Samjnitaha. First he talks about something known as Dhruva Samskara Haraka, where the gati of the moon, that is the rate of motion of the moon, has the difference between the rate of motion of the moon and its apogee, that is Tunga means apogee, has to be divided by their longitudinal difference. Then that is known as Dhruva Samskara Haraka, and this Dhruva Samskara Haraka forms as the divisor for the correction, and the correction is obtained like Tungedhike Rinakhyaha Syad Dhanakhyaadike Vidhau Dhruva Samskara Samjnam tu Haraka Dhruvavat Pathet Ratnashreyeti Samshodhya Svodaya Sphuta Bhuktitaha Harakena Vibhajyaptam Swarnam Kuryan Nishakare. Nishakara is the moon. So the true rate of the motion of the moon minus 12 degrees 02 minutes should be divided by Dhruva Samskara Haraka to get the correction to the moon. So here we have touched briefly on the algorithms mentioned in the Vakyakarana, old Vakyakarana, to find the true longitude of the moon, and also the rationale, though I have not discussed, by the Karana Paddhati and the Dhruva Samskara, which is given in Vakyakarana. The beauty of this Vakya system is this does not involve any sine functions, because when you look at the Siddhantic procedure, so in order to obtain the true longitude of the moon, we have sine delta theta is R0 is a function of sine. So though if we approximate this sine delta theta as delta theta, obviously we have to find the value of sine pertaining to theta 0 minus theta u. So without the knowledge, understanding of sine function, just by using basic mathematical operations, addition, subtraction, division and multiplication, we can obtain the value of true longitude of the moon, true longitude of the sun and other planets at any desired date. So this will be useful for Panchanga Kartas, those who are not very good at mathematical computations. So that's how this system got evolved, and as I told, this is originated in Kerala and it's more popular in Tamil Nadu, which is known as Pambu Panchanga or Vakya Panchanga. Thank you.
Yogi Ramsuratkumar, Yogi Ramsuratkumar, Yogi Ramsuratkumar, Jaya Guru Raya. Thank you so much, Dr. Pai, for a very, very enthralling and scintillating session.